Hi everyone, in this video I will continue with the design and analysis of shallow foundation focused on the topic of consolidation settlement. So consolidation settlement occurs over time in saturated clay soil. Right? So the focus of the consolidation settlement is in the clay soil and it is subjected to an increased load that caused by constructions of the foundation. So we have the foundation here and we have the clay layer underneath the ground surface. So for the consolidation settlement, it will happen in the clay layer. So we have three different equations here for normally consolidated clays and for over consolidated clays. Note that the increase in effective pressure, delta stress prime, on the clay layer is not constant with depth. The magnitude of the delta stress prime will decrease in depth measured from the bottom of the foundation. Alright, from the bottom of the foundation, you can see that the decreasing of the delta stress prime. So you can see here that we have the delta stress prime T is T for the top layer. Okay, at the clay layer section, and then we have in the middle and at the bottom part of the effective pressure. Right, so this is the equation again. So for the normally consolidated, we have all these kind of parameter that we need to identify. Alright, so we have the CC. What is the CC? CC is the compression index. The HC is the thickness of the clay layer. The E naught here is the initial void ratio of the clay layer. And then we have the delta, we have the stress prime naught is the average effective pressure on the clay layer before the constructions of the foundation. And we have the delta stress prime average is the average increase in effective pressure on the clay layer caused by the constructions of the foundation. Right, so what is the difference? The initial is before the constructions and the delta stress prime here is once we have the constructions of the foundation. What is the difference between these two equations for over consolidated clays? As you can see here, there are two requirements. So if you have the pre-consolidation pressure is larger than stress prime naught plus with the delta stress prime average, so you can use this equation. Otherwise, if the pre-consolidation pressure more than delta stress prime, but then it less than stress prime plus delta stress prime average, so you will use this equation. So actually, where that we can obtain the data on the value for sigma prime C, pre-consolidation pressure, the compression index, the swelling index, the initial void ratio is actually extracted from an odometer test, one-dimensional odometer test. So once you analyze data from an odometer test, you plot the graph so you can determine the pre-consolidation pressure, the compression index, and also the swelling index. So what kind of the data? So it's just like a recap how to obtain those parameters. For example, here, if we want to determine the pre-consolidation pressure, the data from an odometer test, you need to plot the void ratio versus the log effective stress. So by using this graphical method, so you can see, you can get the pre-consolidation pressure. Also, you plot the void ratio again with the log stress. So you can get that the compression index here is at the slope area here. So this is the compression index, and when it's unloading the load during the odometer test, you can get the swelling index here, CS, so also known as the compression index. Alright. Okay, now we go straight to an example, so it's more easy to understand. So now we have an example of a plan of a foundation with the size of 1 meter times 2 meter as shown in this figure. So we need to estimate the consolidation settlement of this foundation. So all the parameters, as you can see here, we have the net stress increase, the Q naught, and then we have the unit weight for the sand layer, and then we have the groundwater table. So be very careful with this groundwater table. So we need to consider with the gamma saturated here. And we have the clay layer. It mentioned that it's normally consolidated clay with all the informations of Young modulus, cohesion ratio, void ratio, compression index, and swelling index. And then don't forget, look at the thickness of each layer. Okay, now we look at the solution for this exercise. So first, we need to identify the equation to be used. Okay, now the keyword here is it is normally consolidated clay. So this is the equation for normally consolidated clay. So we need to identify all the parameters that we need to be used. We have the compression index, thickness of the clay layer, the void ratio, stress initial, and then the delta stress. Okay, now we determine the stress prime naught first. So it's basically by using this equation, which is the unit weight times with the thickness for each layer. So we will determine it until the middle of the clay layer. So that is how we will do it. And we need to consider the groundwater table. So you can see here that we have this equation. Okay, so this is for layer number 1. You can see that the thickness is 2.5. So 1 meter here plus 1.5 meter still in the first layer. And then we have unit weight is 16.5. So this is the 16.5. Alright, then we go to the second layer. Remember that we have the groundwater table here. Okay, we have the groundwater table here. So we need to consider the thickness is 0.5. And then we need to use the gamma prime. Whenever we came across with this kind of groundwater table layer, so we need to use gamma prime, that gamma saturated minus with gamma water, unit weight of water. So this is the unit weight of water, this is the gamma saturated for the second layer that underneath the groundwater table. Then at the third equation here, we have 2.5 divided by 2. As I mentioned that we need to get the delta stress initial, we need to determine the stress prime naught here until the middle of the clay layer. So we have 2.5. So we divide it by 2, you will get 1.25. Okay. So this is the middle line for the clay layer. And then you have the unit weight is 16 here. Still, it is under groundwater table. Alright, so we need to consider that situation. So the 16 is minus with the ground unit weight of water 9.81. Then you can get the stress prime naught here. Okay, the effective pressure on the clay layer before the constructions of the foundation. So this is the effective pressure before the constructions of the foundation. Okay, what's next? So now we need to determine the delta stress prime using 2-1 method. So this is the distributions of the stress change underneath the foundation by using the 2-1 method. Alright, so we need to project below the foundation. Okay, just like this, B plus Z. Z is the depth. Alright, so we need to use the concept or the rules of 2 to 1 to find the stress increase under a foundation. Okay, let's take a look. Alright, so in this, we already have this one. So we need to identify for delta stress prime here. Okay, so look at this diagram. You can see that I project a vertical line here below the foundation, below the base of the foundation for both sides here. Okay, then we project this line. Okay, now we need to use the 2 to 1 method. Okay, so this is the size of B. Okay, at the base of the foundation, the size of foundation. All right, so when we go down here, so it's still B size. All right, by using 2 to 1 method. So for example, we note here as X, and also this one is X. And we label the vertical line here is Y, for both sides is Y. So based on the concept 2 to 1, so if you have X here, okay, so 2X here will equivalent to Y. Okay, 2X here will equivalent to 1. Okay, because this is X, so the length of the vertical line here is 2 times X. Alright, so this is X. So the length of the Y here is 2 times of the X here. So that's why 2X will equal to Y. Alright, so now we can say that the total length of the stress increase below the foundation here is actually B plus Y, because we have 2X here. X plus X will become 2X, and 2X is equivalent to Y. So the stress increase, the length here is B plus Y. Then in L direction, it will have L plus Y. So this area at bottom of the stress distribution diagram here, by using 2 to 1 method, you can get the area is B plus Y times with the L plus Y. Again, so this is the Y. So Y is the distance from base of the foundation to the mid plane of the clay layer. Alright, so remember that we project all this line is until the mid layer of the clay. Okay, now the Y, the value of Y, okay, you can get here below, okay, directly at the base of the foundation here. So we have 1.5, okay, plus with 0.5, and then plus with 1.25. So this is the length of the Y. So Y is 3.25. Alright, so now we want to identify, or we want to determine the delta stress prime here, which is the increase in effective pressure on the clay layer caused by the constructions of the foundation. So now in this case that we assume that foundation, we have constructed the foundation. So what will happen in this effective pressure? Okay, now we want to determine the delta stress prime average here. So we want to identify the average increase in effective pressure once you constructed the foundation. Alright, so it's actually based on the basic equations, force over area. So we should have the equation unit, that kilonewton per meter square. So how we can get this one? So we have the net stress increase here, Q naught, and we can times with the area of the foundation, B times L here, and then we divide it with the area at the bottom of the stress distribution. Okay, at the stress distribution. Okay, so we have 150 kilonewton per meter square times with the B times L, the size of the foundation, and then the area at the bottom of stress distribution, alright, at the clay layer part. Alright, so we have B plus Y times with the L plus Y. So we can substitute all the values. So we have the B size of the foundation is 1 and the length is 2 meter as given here. And then the B plus Y, so we know that Y just now is 3.25, so we have 1 plus 3.25. 1 here is B, and then 2 here is L, plus with the Y is 3.25. Alright, okay, so now we can have the kilonewton the upper part here. Alright, so 150 times with 2 is 300 kilonewton. And then you solve this one. So you will have the area is 22.31 meter square. So you can get the average increase in effective pressure on the clay layer caused by the constructions of the foundation is 13.45 kilonewton per meter square. Alright. Okay, now what is the next step? So now finally we need to determine the SC. SC is the consolidation, C is for the consolidation, S is for the settlement. Okay, back to this equation. So the calculated parameter just now are the stress prime naught here and delta stress prime. So this is the initial before the constructions of the foundation overall, and this is when we consider the constructions of the foundation. And then we also have the given information. As you can see in the question, we have the void ratio 0.8, the compression index is 0.32, and the thickness of the clay layer, the overall thickness of the clay layer is 2.5 meter. So now we can use directly this equation. So we have the CC here is 0.32, the HC, the thickness of the clay layer 2.5, the E naught is 0.8, and then stress prime naught here is 52.84, and then delta stress here is 13.45, and then divide by the stress prime 52.84. So at the end you will have the SC or the consolidation settlement is 0.0437 meter, which is equivalent to 43.7 mm. So the consolidation settlement at the clay layer here is 43.7 mm due to this size of the foundation. So this is how we calculate or we determine the consolidation settlement.